Hello class, and welcome to this lesson on 8.5. We're going to be talking about the chi-square test for variance or standard deviation. This is going to be the last lesson in the chapter. So the question is, what is the specific statistical process for testing hypotheses involving variances or standard deviations? So the learning goals of this lesson are to calculate a chi-square test statistic, find critical values for chi-square, find rejection regions, and use a chi-square test to test a population variance or population standard deviation. All right, so the vocab includes the chi-square test as well as the chi-square distribution. All right, so to quickly review what we have covered in the previous lesson. So remember that we covered tests for means as well as tests for the proportion, which is the z-test for the proportion last class. So we looked at tests for the mean and a test for proportions. So quickly running through those, remember that the z-test for a mean can be used when the sample size is large enough or when the population is normally distributed and the population standard deviation sigma is known. Now, if the sample size is small, then we use a t-test, and that was used when the sample size is small and the population standard deviation was unknown. And then the most recently, we did the z-test for a proportion, and that was based on the binomial distribution, success or failure. So it must satisfy those properties, as well as the fact that the sample size has to be large enough, which in the case of the z-test for a proportion, np is greater than or equal to 5, or nq is greater than or equal to 5. They both have to be satisfied. So now we're going to talk about the chi-square distribution. So we talked about the z distribution and the t distribution. Remember that the t distribution was a family of curves, unlike the z distribution, which was just a single curve. Well, similarly to the chi-square distribution is similar to the t distribution in that it is actually a family of curves. So up to now, we haven't really discussed claims involving the variance or the standard deviation. We've only done the proportion and the mean. So we're going to start looking at those today. Remember that the variance and the standard deviation represent the spread. So in this case, we're interested in claims about the spread of the data, how the data is spread out. So just like the t distribution, the chi-square distribution is a family of curves based on the degrees of freedom calculated in the same manner. df is n equals n minus 1. So, but unlike the t distribution, the chi-square distribution is not symmetric. It's actually positively skewed or skewed to the right. So because it's actually squared, this is why it's actually called chi-square. So notice that this symbol right here is the Greek letter chi, this X-looking symbol, right? And then there's the squared there, so that's why it's called chi-squared. So the Greek letter chi, in this case, is not chi or x squared, it's just chi-square, is going to be used for this type of test when we're dealing with standard deviations or variances. But notice that that value is actually squared, right? There's an actual squared there. And remember that a squared value can never be negative if you're talking about real numbers, right? So therefore, the same thing applies to the chi-square distribution, is that since it's actually squared, this is why it's not symmetric, because it doesn't have a negative side because it's squared. So anything that is negative that is squared makes it positive. So the smallest chi-square value you can have is actually 0. Similarly to other distributions, the area under the curve is 1. So that's the same property. So we're going to show you how this actually looks like, how this actual curve looks like in the demonstration below. So notice that it's a family of curves, right? That is, and the type of curve that you choose depends on the degree of freedom which is based off of the sample size. So if I selected a sample of 25 people, then my degree of freedom is going to be 25 minus 1, or 24. And therefore, I'm going to choose the chi-square curve that has 24 degrees of freedom. In this case, I gave you 3 examples, one with 1 degree of freedom, 5, and then 10 degrees of freedom. All right. So now how do we find the critical values for chi-square, just like we normally do for the other curves? Well, unlike the tables for z and t, the chi-square table gives you areas to the right, not to the left. So the other, the z chart actually gives you the areas to the left, right? So we got to be careful with this because it's opposite of what we think now. So we got to adjust our methodology because of that, the fact that it gives us areas to the right. So again, we'll show you just what we mean by giving you areas to the right. So this is the actual graph, an image of a chi-square distribution. So when I draw a generic chi-square distribution, it'll look like this. And notice that it's skewed to the right because you have a longer tail on the right side. And the table, when you look it up, is going to give you the area strictly to the right of whatever your critical value is, or whatever your chi-squared value is. Okay, so how do we use the chi-squared value? Well, we know that the whole thing has an area of 1, right? So this whole thing has an area of 1 underneath the curve. So if they give you the area, to the right, well, I can get the area to the left by doing 1 minus alpha, right? So this area to the left is actually 1 minus alpha. And the area to the right is alpha. It's opposite with the z. Remember, with the z, to get the area to the right, you have to do 1 minus alpha. And to get the area to the left is just alpha. Well, it's reversed for the chi-square. So if we want to use the chi-square distribution appropriately, then we have to make sure that we consider the fact that it gives us areas to the right. So first off, identify the degrees of freedom that you're going to be interested in depending on your sample size. So n minus 1. Then identify what type of test you're dealing with. So if it's a right-tailed test, you're simply going to look up the area alpha from your significance, from your level of significance. So if your level of significance is 5%, you're just going to look up that area in order to find the critical chi-square. All right. If it's a left-tailed test, then you're going to do 1 minus alpha because that's the left side. If you're doing a two-tailed test, well, in that case, you actually have two sides, right? The left and the right side. So in that case, what you would do is you would have to split the alpha into 2 pieces, right? So you're going to have alpha divided by 2. So this is going to be half the alpha on the right side. And then you're going to have another chi-squared right here, another chi-squared value there. You're going to have 2 chi-squared values. We'll call this chi-squared 1. We'll call that chi-squared 2. So 2 of them. Because both tails. And then this side will also be alpha over 2. But remember, in order to get the left side from the table, you have to do 1 minus, right? So you're going to have to look up, for this thing, you're going to have to actually look up 1 minus alpha over 2 to get the left chi-square value. To get the right chi-square value, you're going to have to look up alpha over 2. Okay? So, and that's exactly what it says here. For the two-tailed test, for the left critical value, you look up 1 minus alpha over 2. For the right critical value, you look up alpha over 2. All right? So it makes sense if you look at it in terms of the graphic that I provide here. If you think about it in terms of the picture and actually draw the picture, it was worth 1,000 words here. It actually does kind of tell you what to do. All right, so let's look at the first example. Find the critical chi-squared value for 15 degrees of freedom with a 5% level of significance if the test is right-tailed. So first off, we're going to draw a generic skewed to the left chi-square distribution. So it looks like that. And then we have our chi-squared critical value, which we don't know what it is yet. And then it's a right-tailed test, so we shade it to the right hand side, and then that is worth alpha. So we're going to look up alpha because it's a right-tailed test. Our area that we look up is alpha, okay? If it's left-tailed, 1 minus alpha. All right, so our alpha is 0.05 because that's our level of significance. So, and then we know that we have 15 degrees of freedom. So we don't really have to calculate it. They just tell us the df. The df is 15 right away. We don't have to do n minus 1 because they already tell us what that is. Okay, so we're going to go to our chi-squared table. So for this chi-squared table, they give you the alpha on the 1 column. And on the left side, on the this column here is degrees of freedom. So that's your df. So they tell us it's 15 degrees of freedom. And we're looking for a alpha, or this is our alpha, our area that we're looking for, okay? So this alpha right here is equivalent to our area. So we're interested in 1 minus alpha, right? So, or I'm sorry, alpha, not 1 minus alpha. So we're interested in 0.05. Okay, so we're going to go ahead and figure out the intersection of those two. There you go, and that's my critical chi-square value, 24.996. All right, and that makes sense because that number is large and we are all the way to the right of the curve, 24.996. Again, remember, this is going to be 0. The smallest chi-squared value you can get is 0. You can't get any negatives. Notice that there's no negative side to this graph. All right, and that's how we get the critical value. So let's look at another problem. Find the critical chi-square value for 10 degrees of freedom. So df is 10, and the test is left-tailed. So since it's left-tailed, that means that we're going to look up our area. Our area is 1 minus alpha. So it's going to be 1 minus, and our alpha is 0.01. That's my alpha. So it's 1 minus 0.01, which is 0.99. Okay? So we're going to look that up on the chart. But of course, we're going to draw our generic chi-square distribution. And then we're going to shade to the left, okay? So this is alpha, right? But we're going to look up 0.99 to get that actual value, okay? So we're going to look up 0.99 and it's 10 degrees of freedom. So again, this is 0.99 and 10 degrees of freedom. So it looks like our chi-square critical is 2.558 based off of the chart. Okay, so we're going to label that on our chi-square, and that number makes sense because we're very close to the 0 mark. So 2.558, I believe it was. Okay. All right, so we're good. Let's go ahead and zoom out here. All right, and that's our critical chi-square value. All right, let's do another example. This time where it is it's actually a two-tailed test. Now, there's one thing I need you to keep in mind, and that is the last bullet point here, which is if the exact degrees of freedom cannot be found on the table, which that will happen occasionally because the table only gives you a limited amount of values. But if the exact DF can't be found, then the closest smaller value should be used. So the reason why we use the closest smaller value is because it's better to restrict yourself on the degrees of freedom than to allow yourself more freedom. Okay, so it's better to be conservative in your estimate than it is to be liberal in your estimate as far as, when we're talking about over or underestimating. Okay, so we're being conservative here, and we'll choose the closest smaller value in this case. Okay, so if we have, for example, well, we'll do an example. Example 3 will actually go actually use this bullet point. Okay, so here our degrees of freedom is 33. So we have df equals 33. We got 5% level significance, so that's my alpha. And it's a two-tailed test. So we know that when we draw our chi-squared, we're going to have two criticals, right? We're going to have one on the left, one on the right. So, and then both sides split the alpha. You're going to split the alpha between both sides. So instead of both of them having 5%, both of them are going to have 2.5%, right? So that's why it's alpha over 2. So each of these is 0.025, and this is 0.025. That's what the area underneath is worth, right? But to look it up on the table, for this right side, we need to look up 0.025 because the table gives us the area to the right by default. Okay, if you don't remember, if you use this chart, it actually shows a diagram here on the bottom right hand corner, and it specifically tells you, hey, this is the alphas that are given in the table are the areas to the right, not the left. Okay, so look at that chart, and that actually tells you the area that it's giving you. So that means if we're looking for the right area, just look up 0.025 in this case. If you want to look up the left area, then we got to look up 1 minus that. Okay, so we got to do 1 minus that number, and that will give us the left area, which is 0.975. Okay, so look up both of those values, and then we'll be able to find our chi-squareds. Okay, so 0.025, 0.975, and then the df is 33. Okay, so let's go to our df for 33. I'm going to circle it because I know I'll forget it. All right, so looking at this case, like I mentioned earlier, looking at the chart, you're not always going to have all the degrees of freedom there. So what you're going to do is you're going to look at the closest smaller one, right? So the closest smaller one is going to be 30. All right, so we're interested in doing 30. Now, even if you had 38 degrees of freedom, you still want to choose the closest smaller one. So you still want to do 30. Okay, so be very careful. It's better to be conservative with your estimate than it is to be liberal with it. Okay, as far as calculations are concerned. So the closest smaller one. All right. So choose 30. So I'll put a little asterisk by there because that's important. All right. So in this case, we have 30, and then let's go up to the columns here, to the top row. So we're interested in 0.975 and 0.025. So we're going to trace those down because I don't want to lose sight of them. All right, so it looks like we're using 16.791 and 46.979. So 791 and 979. All right, and that makes sense because that's the left and the right side. We're left and the right side, so that does make sense. That the far right side is going to be a large number, 0.46 or 46, I mean. All right, and those are my critical values for the chi-square. All right, so now we're going to show you how do we set up hypothesis statements for chi-square. So when you're using chi-square, remember that the chi-square is for the variance or the standard deviation. Now, what is the variance? The variance is the square of the standard deviation. So remember, the standard deviation is a measure of spread. So if my measure of spread is on average 5 units per number on average, then my variance is going to be 25. 5 squared is 25. Okay. So the standard deviation is the square root of the variance. Okay. So the symbol for standard deviation, the population is sigma. So this is the standard deviation, and then sigma squared is variance. Okay, so you just got to square the number. All right. So when we're writing hypothesis statements, what we're going to do is we're going to be using the variance instead of the standard deviation. So for example, sigma squared equals 225. Sigma squared is not equal to 225. So we're using the variance here rather than the standard deviation. Okay, just to keep things the same, uniform throughout. All right. So next what we want to do is we want to show you the conditions. So if we want to use a chi-square test, then we just like the other tests, there are conditions that need to be met. First off, the sample has to be randomly selected, which is true for all the tests. Whenever you take a sample, it has to be random. In addition to that, the population must be normally distributed, as it usually has to be, and the observations has to be independent of one another. Okay, so we'll assume that those conditions are met when we do our word problems. To find the test statistic, that's given by this formula here, n minus 1 times f squared over sigma squared. So that's our formula for the chi-squared test statistic. All right, so the steps are going to be the same other than the formula. You're going to write your hypothesis statements just like we normally do. Then you're going to identify your level of significance alpha. You're going to determine your test directions, sketch your curve, find the critical values, which is what we did earlier in the previous problem. shade your rejection regions on the chi-square distribution. That should be chi-square distribution, not t distribution. Apologize for that. And then you're going to calculate your test statistic using that formula, make a decision, and then you're going to do your conclusion, your final conclusion. All right, so let's look at an example to see how this works. So according to a College Board study, the standard deviation for the math SAT is 100. An instructor thinks that the standard deviation of the 23 randomly selected students in her school is less than 100. The variance for the 23 test scores is 72.25. Is there enough evidence at the 5% level of significance to reject the College Board's claim? Assume the variable is normally distributed. So they give us variances and standard deviations here. So we got to be very careful, okay? So first off, it says that according to a College Board study, the standard deviation is 100, okay? So that's our claim right now. So they're saying that the sigma is 100, the standard deviation. All right, so that's the claim. However, when we set up our hypothesis statements, we want to do it for the variance, right? Just to keep things the same. So I'm going to go ahead and convert this to a variance, okay? All I got to do is just square it. So what's 100 squared? So all you got to do is just add a couple zeros, okay? So 100 times 100 is 1 with 4 zeros. So it's 10,000. 100 times 100 is 10,000. So our claim is that the the variance for the math SAT is 10,000. Okay, so let's write that here as our claim. The claim is that the variance is 10,000. So you just got to be careful with variance versus standard deviation. An instructor thinks the standard deviation is less than 100. So the instructor thinks it's less than, that the variance is less than 10,000 basically. All right, so this claim is a statement of equality, so that belongs to the null. Now the instructor is the researcher here. The instructor thinks that it's less than 100. It should be less than 100. So that's going to be our research hypothesis, which is that the sigma squared is 10,000, less than 10,000. So based off of this is a left-tailed test. Okay, so we're going to go ahead and write left-tailed here. And the alpha is given in the problem, 5% level of significance, so 0.05. All right, so we got everything that we need here. We went ahead and I went ahead and provided you with the chi-square curve. Notice that when you draw it so it's skewed to the right. Okay, so since it is a left-tailed test, that means we're interested in some kind of chi-square value here, some kind of critical value there. And I'll go ahead and shade the area to the left here. So that area right now is 0.05. But since the chi-square gives us the area to the right instead of the left, I got to do 1 minus, right? So I got to look up 1 minus 0.05, which is 0.95. Okay, so that's what I got to look up. Let's go ahead and calculate our degrees of freedom, because I forgot to put this as a step actually. So for step 2, it should say, I'll go ahead and adjust this real quick because I forgot to put this in here. Step 2 for chi-square test, identify level of significance and determine your DF, which is n-1. I forgot to include that, I apologize. So determine the n-1 and your alpha. Okay, so let's go ahead and do that right now. So the DF here is n-1. How many people did we survey? Well, it says we surveyed 23 random people, so students. So it's 23 minus 1, which is 22. Okay, so that's my degree of freedom. So 22, and then we're going to look up 0.95 in our chi-square table, which I provided right here. So 0.95 and 22 people. So looking at that area, that's about 12.338. I'm going to go ahead and provide that right here. All right, so now we got our curve. And let me just write that here. Okay, so we shaded the region. We're good with that. So now we're going to calculate the chi-square test, which remember it's n minus 1 s squared over sigma squared. So n minus 1 is 23 minus 1 s squared. So what is s in this case? Well, s is the sample variance. Okay, so it says here that the 23 students were selected. And it says that the variance of the 23 test scores is 7,225. So that variance is the sample variance. That's s squared. The sample variance is, the square of the standard deviation from the sample, the students. So that's my s squared, 7,225. So we got here 7,225. Divide that by the sigma squared, which is 10,000. So it's not a very hard calculation. There are no square roots or anything that you have to deal with, so that's good. So I got the chi-square test, the test statistic to be 15.895. All right, so that's my chi-square. Now, if I label that on my curve right above, well, that's going to be right here. I was trying to do a different color. There you go. So that's 15.895. So that means that I'm outside my rejection region, which means that I'm going to fail to reject here. So that means I don't have enough evidence. There is not enough evidence at the 1% level. Now, our claim belongs to our null hypothesis, so we're going to use the word reject to reject the claim. To reject the claim that the standard deviation of the math SAT test is 100. All right, so let's look at example 5 real quick. So for this one, it says a hospital administrator believes that the standard deviation of the number of people using outpatient surgery per day is 8. So we have the standard deviation is 8. That's a claim. So let's convert that to a sigma squared. So that's going to be 8 squared, and 8 squared is 64. Okay, so a random sample of 15 days is selected. So it looks like n to me, n equals 15. The standard deviation was found to be 13.5. So from the sample. So that means that's the sample standard deviation. So that's S. So S is 13.5, which means we're going to have to square that to get the actual variance here. When we do that, we get 182. S squared is 182.25. Okay, so that's my sample variance, S squared. We're going to need that later. But let's go ahead and do our claim. So the claim was from the administrator. The hospital administrator believes that the sigma squared, the variance, is 64. So that's a statement of equality. So we're going to put that under our null hypothesis. And since they don't really tell us what direction, whether it's greater than or less than, we're going to say that the alternative is that is not equal to. All right, so now we have our alpha, which is 10% level significance right there. So alpha is 0.10. So the direction of our test, based off of the fact that it's not equal to for the alternative, we're going to say it's a two-tailed test. So that means we have two chi-squared values that we got to look up. Now the area on each side, remember, we got to do alpha divided by 2 here, which is 0.05, right? So each of these areas is worth 0.05. But that doesn't mean we're going to look up 0.05 on the table for all of them, right? For both of them. So for this one, since it's on the left side, we got to look up 1 minus 0.05, which is 0.95. So we're going to look up 0.95 on the table, whereas this one, we're just going to look up 0.05. Now, we need to do our degree of freedom, which is n minus 1. It looks like from the problem that 15 days was selected. So we have 15 minus 1 is 14. So we're looking at 14 degrees of freedom, 0.95, 0.05. So we're going to go over here. Went ahead and already selected those just to kind of save us a little time. But we have 0.95 here, 0.05, 14 degrees of freedom, and then we got our two critical values, 6.571, 23.685. Let me go ahead and write those values down real quick. All right, so those are my two criticals. Okay, so we got that. We shaded our region. Now we're going to do our test statistics. So remember the formula for that, n minus 1 s squared over sigma squared. So our s is, or our sample size was 15 days, take away 1. And then our s squared was the 13.5 squared that we had here. So it's 182.25. And then our sigma squared was from our claim, so that was 64. I'm going to go ahead and calculate this. Oops. So I get about 39.867. Okay, so that means that, oops, I'm going a little bit too far here. So 36 point, that's all the way on the right side. So that's all the way over here, around there somewhere. So we're definitely in our rejection region. So we're on the right rejection region. So therefore, we're going to go ahead and reject. All right, so we went ahead and rejected. So that means that there is enough evidence at the 5% level to, and in this case, our claim belongs to our null. So we're going to use the word reject. Reject the claim that the standard deviation of the number of people who use outpatient surgery is equal to 8. All right, guys, that's it for the lesson. I hope you learned something from this video. This is the final lesson in the unit, so nothing too crazy, just a bunch of tasks that we talked about in this unit. As always, I'll see you guys in the next one.